seminario del 2025. Gracias por venir. Es un gusto tener con nosotros hoy a Carlos Doñate, que viene de la Universidad Jaime I de Castellón a darnos este seminario. Voy a hacer una breve introducción sobre su carrera científica, porque aunque es un investigador joven, si se me permite decirlo, pues ya ha hecho muchas cosas y tiene una carrera bastante contrastada en su tema de investigación. Él hizo el grado de física en la Universidad de Valencia y realizó también un primer máster allí y luego un segundo en la Universidad Jaime I de Castellón, donde después hizo la tesis doctoral que leyó a finales de 2019 y estaba relacionada, de hecho, con la formación de nanopartículas en líquidos por láser. En enero del 2020 se fue para una estancia postdoctoral a Essen, en Alemania, en el grupo del profesor Barsikowski, que es bueno, una personalidad, vamos a decir, el más importante en este tema de investigación, y en el año 2021 se trasladó a la Universidad de Wuppertal, donde bueno, siguió trabajando un poco en un tema relacionado también a nanopartículas, pero metiendo el additive manufacturing de polímeros, que de hecho va a hablar sobre esto también en la presentación de hoy. Y allí, bueno, pues fue un líder de grupo con estudiantes a su cargo, proyectos de investigación a su cargo. Y ya en el año, a finales del 2023, o sea, lleva poco más de un año, volvió a la Universidad Jaime I con un contrato de atracción de talento de la Generalitat Valenciana. Bueno, ha publicado muchos trabajos en el tema, algunos nos los va a contar aquí. Está muy involucrado en el tema de las partículas en líquidos, no solo a nivel investigador, sino también en organización de reuniones científicas, congresos. No sé si dirás algo al final, también hacer publicidad. Y bueno, es un gusto tenerte aquí, así que cuando quieras.
Thank you everyone for your attendance, especially to Esther for the invitation and to Javier. It's a pleasure to be today here at CSIC, and my talk, as Esther was mentioning, so I have had a career that has evolved well from Spain, some postdoctoral stays outside, and also evolving in the topics that I was developing. And I wanted to start the talk also making a bit of showing you also, especially for those of you that are doing the PhD, for example, sometimes we are a bit lost on what to do after, which options we have. Of course, this is not the only option, but I wanted to show you briefly my career steps. So as an example, so yeah, I started in Valencia. I did a PhD in University Jaume I. I was mostly working in optics, doing the synthesis of nanoparticles with ultrafast lasers. And then I moved to Germany, where I started working also in additive manufacturing. And that was really enriching. So my period in Germany, I could learn about additive manufacturing. I was lucky that it was in combination with the generation of nanoparticles with lasers. And then I had the chance just last year, so I'm here for 1 year, to return to Castellón and also to bring this additive manufacturing expertise, or to start a new research line at the institution, at the University Jaume I. So some introduction, because well, Castellón is not so well known. When I tell about it in Germany, they don't know where it is, either the one coast or the other, or north or south. In Spain, I guess you can locate it, but it's not the biggest city. So we are Valencia, of course. We are a small university, so it's quite young. In fact, the university is my age. But there is, well, quite a lot of research actually, and quite a lot of development, and specifically in our group, in the GROC UJI, the group of research of optics. We have, in fact, quite different research lines from different researchers from Ramón y Cajal and different contracts. So the, let's say, basic or the starting lines in the at the university were this computational imaging, so mostly imaging through turbine media, for example, scattering media, controlling these effects. We have also a line of phononics that was recently, some years ago, with a Ramón y Cajal contract started. Also frequency comps, applications. Another of the traditional lines was the complex beam shaping, and in fact was the starting of the group. And some years ago, like 10 years ago, so Gladys Minguez, she started the line of the synthesis of nanomaterials with pulse lasers. And now with my incorporation, so we are starting this new extra line of additive manufacturing in combination with the nanoparticles. Okay, so this is like a picture I will show 3 or 4 times during the talk, so just to locate where we are. Basically, the approach that we were doing in Germany, now we are doing in Spain. The approach we are following is generation of nanoparticles with laser. As you can see here, I will be talking at the beginning of the talk about improvements of this technique. I will show you the principles also, because some of you may not know about it. And then the idea, or one of the applications that we are developing, is to take these nanoparticles that we have produced, like here, the colloidal nanoparticles, and then add them to different materials that are already used in additive manufacturing, like powders, photopolymers, or, well, we can also generate filaments, for example. Then the idea is, once we have modified these materials, to use the standard 3D printing technologies. So you may know already about filament printing, polymerization, laser powder bed fusion. So we have different techniques, and we can produce functional materials by this, let's say, intermediate step of adding the nanoparticles into the common materials. First, maybe very general introduction. This you have it already in mind, but why nanoparticles? So we started doing the nanoparticles by laser, but why are they interesting? Well, they are in a size range that is quite interesting for bio applications, because they can interact with many bio entities, let's say. But also, due to the size reduction, the nanoparticles get different properties compared to the bulk materials. For example, optical properties, like you can see here. As you usually see silver or gold, you see the typical metallic response, the reflectivity that you expect from these materials. When you reduce them to the nano size, you get these plasmonic effects. And you, for example, can see here colloidal nanoparticles from silver. These ones were synthesized by laser ablation liquid. These are gold colloidal nanoparticles. And already, as historical mention, so these nanoparticles are not new, of course. We are always breaking things, generating smaller parts. And already from the Romans, they were using, or they found these kind of structures in this famous, at least for the nanoparticle community, Lycurgus cap. So that you can see that the color of the cap depends on the illumination. And they could find this kind of structures, and are the optical properties of these, the special properties of this cap are related to them. One topic that we like a lot, because we come also from the optics group, so it's to combine it, not only to generate the nanoparticles with laser, but also to provide extra properties, extra optical functionalities, like, for example, fluorescence. So I will show you some applications of nanoparticles we can generate that have this fluorescence and what they are using for. And another 2 topics, I mean, there are a lot of topics where you can apply the nanoparticles, energy harvesting, many functionalities that you can provide. But for example, in catalysis, they are very useful nowadays, and they are explored, largely explored. And the main purpose, or the main motivation for using these nanoparticles, is that, well, in principle, we can reduce the size, and then we can maximize the surface to volume ratio. So then if you have more surface, and this surface is empty, let's say, or it's clean, let's say, so it can react, we can achieve a better efficiency of these catalytic processes. And finally, I was showing this magnetic response. Of course, reducing the size, we can also modify the magnetic properties of the materials, and we can also make use of them for example, here you can see an actuator. But let's go to the technique, because I'm telling about it, but I'm not showing you the exact technique. So here you can see the basic principle, then the implementation is a bit different when we want to go for high productivity, but the basic principle is pretty easy. So we can take a laser source, we focalize it or not, depending on the fluence and the intensity we need. And basically we want to do like when we are marking a surface, when we are using the laser to make a mark on the surface. But in this case, usually when we are marking the surface, we care a lot about the material itself, so that the mark is quite controlled, the movement of the laser, the, let's say, borders of the mark, that we don't have many impurities. But in this case, we are more interested in the material that is coming out of the surface of the target. So this material that is coming out is collected in the liquid. And here you can see the easiest implementation of the technique. We can just take some water, some liquid, we can add the target, and then we do the ablation with the laser. And then you can see that directly the material that is expelled is collected as nanoparticles. In this case is gold. You can see that we have the typical plasmonic response. We can see the red coloration of the nanoparticles we are generating. This technique, well, looks very easy. That's very good. Here you can see another example of the implementation. It requires some investment, of course. You need the lasers. That's the biggest investment. The gold is also expensive, but you can also do it with other materials, as I will show later. Just some advertisement also of the group at the university. So these are the laser sources that we currently have. Two of them are quite new. So we can range from the standard nanosecond lasers at 10 Hertz. And now we have newer laser sources like this Monaco, that is, the pulse duration is tunable. We have 60 watts power, and the idea is to use this source mostly for high productivity of the nanoparticles for applications. And then we also have one femtosecond laser, quite a short pulse duration, 35 femtosecond at 5 kilohertz, and it has 10 watts. So it's quite powerful, let's say, for femtosecond and with a short pulse duration. It can be used for the nanoparticle generation also, because it can generate different effects, because the interaction with the material is different depending on the pulse duration. But it can also be used, and it's quite useful for processing, for example, standard processing and marking of materials. Okay, why generating the nanoparticles with laser? Because, well, we can generate them with chemical methods. That's pretty standard. But the laser has some, of course, disadvantages and some advantages. If we only have advantages, then the technique should be all around, and there should be no chemical methods used. The advantages, I want to sell them first. Later I will tell you the disadvantage and trying to find a solution. But the advantages, usually you have seen that we only need the liquid and we need the target. So that's pretty good, because when you are synthesizing nanoparticles with a chemical method, usually you need a reaction. So in this reaction, you have some products also, and not all of them are useful. So you need some purification in the step. So to, for example, clean the surface if you want them for catalysis or for bio, especially because it's quite critical, the purity. Here you can, for example, as I will show, the typical example is gold in water. You know that you will only have gold and water, unless you have some impurities in water itself, but it's quite controlled. The nanoparticles are typically quite stable. That's because of the mechanism, the formation mechanism. So you are generating a plasma that is highly charged. And finally, the surface charge of the nanoparticles is typically higher than with chemical methods, so the zeta potential, basically. And also, you can have the chance also of functionalizing your nanoparticles directly. So, for example, I will show later, we can use, instead of water, for example, polyethylene glycol with some nanoparticles, and then, because we want these polyethylene glycol groups to be on the surface of the nanoparticles, we can just use the material, the base material, and do it in this liquid so that we can get some functionalization. Of course, it has limitations, but it's giving you this freedom. Okay, the technique seems pretty easy, seems quite easy to operate, right? But at the end, if you check the different parameters that we have in the technique, as you can see here, we have a lot of different parts that are coming together. So we have the target itself, that it can be a bulk target, but it can be also microparticles, for example, or even nanoparticles that we want to control the size. We have the scanner because, well, what I have shown, you have seen that the laser was moving. We need to scan it, because if we just send the pulse into the same spot, we will, at the end, we won't be generating any more nanoparticles, or the productivity will be quite low. The liquid itself, the laser is also interacting with the liquid. I mean, we need to reduce the absorption of the liquid, or we need to try to handle this somehow. The chamber, when we want to scale up, we need to go more into the engineering, fluid mechanics, and these approaches. And the laser source, of course. So we need to control which pulses are we using, which pulse duration, which power, which repetition rate. So we need to adjust everything so to try to generate the nanoparticles we want, and ideally maximize the productivity, because, well, if we want to use it in some industrial application, or we want to go to the market, so that's pretty important if we can reduce the price always, or we can maximize the efficiency of the process. In that sense, for example, We were generating iron nickel that I will show later with 100 kilohertz laser, 10 watts. It's pretty standard laser. For some people it's high power, for some people it's not, depending. And we could generate approximately 20 milligram per hour. Only going to high repetition rates and going to higher power using still the same material, we could show that the productivity was increasing up to 400 milligram per hour without changing dramatically the chamber or the liquid or anything else. So the laser, of course, is a big challenge. Everyone wants to go higher in repetition rate, higher in power, but this has some limitations, right? So the industrial lasers, they have a limitation. If you go too high and with very short pulse durations, you can burn everything inside the laser itself. The prices are also going up. So this is really a problem. But this strategy was the one employed in the group I was working as a postdoc in Duisburg Essen. So to, let's say, generate or to achieve the world record in laser ablation liquid productivity. So here you can see a target. Well, you can see it more or less. It's like here below. And you see how the laser is scanning. It's scanning really fast and in a large area. And we are generating all the nanoparticles directly. This is real time, so it's not even fast. What was the trick? Well, one of the problems of this technique is that when you are doing the ablation in air, so you have the plasma plume, and this can also shield your next pulse. But, well, the time of the plasma plume and the spatial distribution of the plasma plume is lower than what we generate in water or in a liquid. When we irradiate with a laser inside the liquid, we are generating a bubble because we are heating, let's say, heating up or we are breaking molecules of the liquid and then we are generating gases. These bubbles are really problematic because we are sending one pulse and then we have this bubble, and when the next pulse is coming, depending on the repetition rate, of course, and how much we are moving, if the next pulse is hitting the bubble, we can lose this pulse. I mean, not lose it, but the productivity is really low because it experiences a lot of scattering. So the approach here was really easy from the fundamental point of view. So it's, okay, let's just go faster. So let's move our laser faster, laser beam faster, so that we can move and the next pulse is going away from the previous bubble. This is easy to say, of course, but they were already using galvanometric scanners that were going at 5 meters per second, even higher. So, well, they needed to go to higher repetition rates or higher speeds, like with a polygon scanner. This, of course, has some drawbacks, that you are losing some energy because the polygon scanner needs to shut off the laser because of the operation principle, that you don't have light going all around like a disco, and that could be problematic with a 500 watts laser. And in that sense, what we wanted to do was to try to increase the productivity, but without using this expensive approach, like using this scanner. So our idea was, okay, instead of using just one beam like we are doing usually, so let's use an approach that is standardly used in laser ablation in air, that is using a diffractive optical element to generate multiple spots. If you have enough energy, that's working pretty good in air, for example, so you can do parallel processing. Here, we were testing it. You can see here, for example, the implementation, so the chambers are a bit more complicated than the initial one you were seeing. But we were testing it and it was working quite good. So we could go from this 400 milligram per hour up to 1.6 gram per hour, only using a higher number of beams. So going from 1 beam to 11 beams. What was the trick? Well, what we were doing was reducing the repetition rate because we were already using full power with 1 beam. So now the problem is not that we have too much power, let's say in that sense. The problem when we use 11 beams is that we will have lower pulse energy. What we were doing then is reduce the repetition rate, reduce the number of pulses, and then each of the pulses will have the same amount as with the single beam. Okay? What's the trick here? If we are reducing the repetition rate, there are less pulses that we are sending, and then the distance between one pulse and the next one is larger. So then we are not scanning faster to move the one pulse away from the next one. We are just changing the parameters. We are playing with a higher number of beams, and we are moving away this bubble. So somehow the principle is the same, but instead of using polygon scanner that is pretty expensive, we are using a diffractive optical element that is just, well, a crystal, a glass that is pretty available. Here you can see a bit the principle. So when we have one beam, so we have the pulse energy, and then we distribute it, or we focalize it in the target. When we have two beams, of course we will have half of this energy. If we don't reduce the repetition rate at the target for each beam, we will have half of this energy, because we are just dividing by two the energy, the initial energy of the laser. But then when we compensate the frequency, so when we reduce the repetition rate to half, let's say that at the beginning we had twice the power as with one beam, but then on the target we will have the same energy as for one beam with each of them. Okay, it's quite, yeah, it's a bit tricky with the wording, but then when you think about it, it's pretty easy, the idea. So this is the example for two beams, and this is the really easy numbers that we were doing. So the distance that we were increasing with one beam, we had a distance between one bubble, let's say, and the next one, or one beam and the next one pulse and the next one, of 7 micrometers. Just by increasing the number of beams and reducing the repetition rate, we could go to 50 micrometers. So this is a big distance, and then we are not losing these intermediate pulses. Of course, it could go higher. It needs to be optimized for each material. Each material has a different ablation rate threshold, so this needs to be controlled individually. But it's a general strategy that if you have enough power, you can apply. Okay. With these numbers, well, we tested for iron nickel, but also for gold, because it's kind of the standard. And we could see that in the case of gold, the base productivity was a bit lower. The increase was also a bit lower, but we could go up to 1 gram per hour approximately, which is quite good for many applications. Maybe catalysis is still lower, but for most of them it's enough. And what we saw is that the differences between the materials, of course, thermal conductivity of the material itself, but also the bubble is different. So for iron nickel, the bubble was slightly smaller than for gold. Then it's easier to overcome the bubble. Okay. Overall, because, well, also in the group in Germany, it was quite industrial application, let's say, or trying to focus on the use of these nanoparticles and the efficiency of the production process. So we were doing a bit of the numbers of the power-specific productivity. We could see that with the diffractive optical element, this productivity was higher. It's true that for the investment-specific productivity, we were still below. But it's true that also that this polygon scanner and this laser that was used in the previous experiments were custom-made, were quite specific. And in our case, it was a laser that is commonly used for glass cutting or for glass processing. So it's a source that is quite available and for everyone. And this is just the last from the laser ablation in liquid part. Just in case you're interested, it's just one slide. So we can do gold, we can do iron nickel, but I mentioned that we can do almost any material, let's say, because in principle, if we can do ablation, we are fine. If we can do it, if the liquid is not absorbing too much. So here I can show you an example. So we were, for example, synthesizing high entropy alloy nanoparticles. So it's like the most standard alloy for testing this iron, chromium, cobalt, manganese, nickel. And the process was really easy, because usually you need some metallurgy alloying to generate the target. But in our case, we were just taking the elemental powders, the iron, chromium, cobalt, all of them, mixing them in a pestle, doing a bit of heat treatment, but just for consolidation, so that the target is not breaking. And then the laser itself is doing the alloying. So we need to be sure that the laser spot is big enough so that it's touching, let's say, all the elements. And then this is generating the alloying of the materials. And finally, the nanoparticles that we generate have components from all the elemental components that we were adding at the beginning. So, well, we can play a lot. With this, you can see that we can generate different alloys, and we have a lot of versatility. Okay, second technique of laser processing. So we can use, I was telling you, we can use a metal target, bulk targets, but for example, for some materials like oxides, for example, this is not so convenient, because we can find them mostly as powders, as micro powders. So it's easier to use them or to use them directly as the powder. We can also do it. So this is called laser fragmentation in liquid. And basically the technique, it's based on taking microparticles or nanoparticles, dispersing them in a liquid, and then irradiating this liquid. This way we can break the particles in a general way, let's say, and then reduce their size, or if we adjust, but this is difficult, but we can adjust also the laser parameters, and in some cases you can also make them grow, for example, because you can kind of melt the surface and then they can go aggregating and forming larger particles. But this is very narrow window. So for breaking, I mean, as everything in life, right? For breaking is very easy. You just put all the energy and then it's breaking. For forming this, melting it and making them grow is more difficult. Here you can see two colloids, two gold colloids. I was showing you that they were red, but of course this plasmonic response depends on the size. So in this case, the nanoparticles were bigger, and then they have this blue coloration. And what we were doing was just to irradiate one of the vessels with our green light, because, well, the gold is quite resonant, or is absorbing quite well in that region when it's going smaller. And then after some time, when we turn off the laser, so you clearly see the optical difference. So basically this is telling us that the nanoparticles are smaller, because the plasmon peak is shifting, and we have returned to the smaller nanoparticles. It's quite visual way to see it. Of course, you can do SEM and TEM and everything and characterize it. What we like, or a material that we like a lot, and I was working in my thesis, and there's a lot of research in the group in this regard, it's carbon. It's quite cheap source. It's quite available. Well, if you treat it well, let's say it's quite biocompatible also. And it's very interesting because when you go below 10 nanometers in size of the carbon particles, you start they start showing fluorescence response. So what we were doing basically, this is, so you can see the setup. So we were doing what we call the flow jet setup. That basically is kind of the liquid is falling, and then we are irradiating while the liquid is falling. The liquid contains the initial carbon. You can see here. You can see here the initial size of the nanoparticle, of the microparticles. So, well, there's a large dispersion, but it's close to 1 micrometer, more or less. And then after irradiation for, well, this was already 15 minutes irradiation. We still had some EDACT. After, this was a long time, but it was also 10 hertz laser. We could reduce the size to, you can see here, all these spots are the carbon nanoparticles. So they are quite well controlled in size, and they are quite small. And one way to prove it, as you see, maybe, yeah, you can think that we don't like TEM or SEM, but seeing things from the optical properties is really easy to check, and really, well, fast way for the screening of the parameters. So what we could do is just to illuminate with a UV lamp, and we could see that the nanoparticles of this colloid was emitting some fluorescence. The fluorescence was quite low. In fact, the quantum yield was 4.5% only. But the good point is that the nanoparticles, these ones were generating in polyethylene glycol, were pretty stable. So there are still samples from my thesis that are still there in the lab. So I went to Germany and returned, and they are still there sitting. With these materials, the first approach was to try to use them as fluorescent labels, so for cell labeling, for microscopy. Yeah, one of the first approaches was to go to the pharmacy to buy some interdental teeth brush, and then we were collecting some oral cells from ourselves. We were doing some incubation with only 40 microliters of the colloidal carbon dots, and we were surprised that we were obtaining a good internalization, because if you see the microscopy images, here you see the wide microscopy, and this the fluorescence microscopy, and you can see that most of the fluorescence signal is coming from inside the cell, so there's not that much outside that area. We were testing it further. Yeah, the animation was important. And well, I always like to show the video. This was just from the same microscopy, just a 3D reconstruction by doing layer by layer of the cells. These were from my PhD supervisor, so I always need to tell. But well, it was quite a lot of fun, and we could also see that the carbon quantum dots were internalizing quite well inside the cells. We were testing also another type of cells with the help of some colleagues. They were doing some culture of these colon cancer cells and lung cancer cells. We were also adding these nanoparticles, and we could see that In the case of the lung cancer cells, we could see quite good internalization all around. I mean, I'm not expert on the bio part, so we can discuss later also, but in the colon cancer cell, for example, we observed that in the nuclei there was not that much of the internalization. So, well, we saw differences, but we saw that most of the nanoparticles were going inside the cell. That was quite, well, interesting from our point of view. And this is very recent. It's also from a thesis that it's ongoing now in the group. But yeah, well, Francis, the PhD candidate, so he was doing also, or he has done a lot of studies to control also the surface of these carbon nanoparticles. So he has been working a lot, adding, for example, polymer layers on the surface of the carbon that he's generating. So to then later functionalize it, for example, with some drugs, anti-cancer drugs like sorafenib. And he could even, during a research stay just last summer, so go and do some in vivo tests. They are still a bit preliminary, but they saw some decrease of the growth of this tumor, like they were showing here. But as I mentioned, it's still quite preliminary, but well, we are optimistic about it, and we are continuing in this direction. And another part of his thesis that I wanted to show with this I close the nanoparticles was about also like sensing, because these carbon nanoparticles are also a good platform for the sensing. So if you can functionalize the surface so that other molecules get attached and affect the fluorescence of these nanoparticles, you can build a sensor basically. So the idea in this case was for glucose, so try to sense the agar. And well, what he was doing mostly was to generate the carbon dots as I was showing with this laser technique, and then doing a functionalization with this boronic acid. The boronic acid is sensitive to the agar presence, and then it's causing some agglomeration of the nanoparticles depending on the concentration of agar that we are adding. This agglomeration is changing the fluorescence of the nanoparticles. And then what you can see here, this curve that you have here, it's basically how the intensity of the fluorescence emission is changing with the concentration of agar. Basically, if you can have a controlled change, that's, I'm not showing here, but it was pretty linear in this range. I mean, of course, that's very important. You can have a good sensor for the glucose in that range. Okay, and now I go to the part of the additive manufacturing. So we are using this generating these nanoparticles. We are using for many things, as I was showing. But my research line that I was doing in Germany and now bringing here was to improve materials for additive manufacturing. One of the parts of additive manufacturing, I like to divide it into polymers and metals because, well, the basis, the fundamentals are a bit more different, let's say, from the material point of view. So from the metals point of view, it's an industry that is quite developed, quite well developed, in fact. There is a lot of money involved, even nowadays. Well, there are medical implants being printed by these techniques, but especially for aeronautics and for different industries that need custom pieces that you cannot, or it's not easy to fabricate in a large scale. And the point is that these materials sometimes, well, also suffer from problems when treated at high temperatures. I mean, not only the metals for additive manufacturing, but generally metals. So when we are bringing them to high temperature ovens, for example, or to, well, in nuclear reactors they are using them, but also for radiation absorbance. But basically you want to improve the mechanical properties of these metals when they are using, or when we are using them in an environment with high temperatures. And one of the ideas that was thought, let's say, some years ago or many years ago was to add like inclusions, add nanoparticles or add particles in the metal matrix. Because when we are breaking a metal, I mean, you can always see, or when we are breaking things, we always see like a crack, right? That is propagating. So the idea is, okay, let's put some things in the middle that are breaking this propagation. So if we have a lot of these inclusions that are breaking the propagation of this crack, then we are hardening, kind of hardening the material also. It's very general, but the idea was to take oxide nanoparticles and add them to the materials, to the powders employed for additive manufacturing. We were taking, as you can see here, the the materials just by irradiation. So we could take the initial material that was larger, we were reducing the size with the laser, and then, as you can see here, the procedure was quite, well, straightforward, I would say. So we could mix the metal powder in a liquid, it's true, so we should be careful also with the oxidation in this case, and control the pH value. So basically the idea is to achieve a situation of pH where we have opposite charges of the nanoparticles and the microparticles of the metal. So that then there is like electrostatic attraction, and then you have supporting through this methodology. The method was working quite well. I mean, the standard method is ball milling or more mechanical based approaches, but the method was working quite well, and we could show that we could add small amounts. Here in this 0.3 weight percent was pretty good dispersion. I mean, you can almost see as these small nanoparticles around. And then when we go for higher, we are just making several layers of the nanoparticles, so they are just kind of agglomerating between them. Of course, what we want is that they are well dispersed, because if we want these, let's say, impurities or these difficulties in the matrix, if we put too much, we will have just balls of the nanoparticles. We were using these small amounts of the nanoparticles, just to show you. Well, here you can see an SEM of the metal. You can see that we have the presence of this yttrium, oxygen also. In the SEM it's tricky to see because the resolution it's quite in the limit of the inclusions that we can add. But below you can see the mechanical response, and at room temperature there is no change adding the nanoparticles, but when we are using them at high temperatures, you can clearly see by in the curve, in the dotted curve, that the response, this compressive stress that could sustain the material, was higher when we were adding the yttrium oxide to the matrix. And finally, I go to the polymers. That's the last topic. And polymers, maybe you are more used to them, because for additive manufacturing is like the standard filaments that we are using, or probably you are using also. You can also use photopolymers. You can use different materials, but there are even nowadays products that are sold that are printed with polymers. Like, for example, in fashion, for example, are quite hot topic nowadays. So there are even some trainings like these ones with these complex, let's say, structures that are printed by 3D printing. But also the idea is to use this approach to generate, for example, scaffolds. So for bone regeneration, so when you need a specific scaffold for one patient, it's easier to produce it with 3D printing than preparing sometimes a mold, especially if the scaffold itself has a complex structure, that maybe doing a mold and an injection is tricky to produce. Of course, for larger scale, the standard techniques are more efficient, are cheaper, but for these custom designs, these approaches are quite interesting. So our idea was the same. So let's take the materials that are used, polymers in powder mostly, and let's add nanoparticles. And the nanoparticles, well, we have a lot of them and with a lot of different properties. So we can do a lot out of it. Of course, it's not just throwing a dice and combining polymer, nanoparticle, and property, doing it with some idea, but the initial idea was, okay, let's try to add the silver, that it has this plasmonic response at 400 nanometers, absorption at 400 nanometers, so that we can increase the absorption of the powder. The problem here was that when we are processing this powder with a laser, usually we need to go to the CO2 lasers, to the infrared region, because they are quite white, they reflect a lot, and then it's more difficult to process them. Well, the basic idea in this case was, maybe, for example, we can use silver. We have a band on 400, and we could use a diode laser in 400. Of course, this can be extended, and for example, using another nanoparticles or another dyes that can improve the absorption, for example, in the near infrared, that we have a lot of laser sources. Basically, what we proved is that we could generate the nanoparticles, mix the polymer powder, and controlling the pH, we could achieve this nano-additivated powder. And as you can see, the optical properties are not changing. So the plasmon peak is at the same position. Since the plasmon peak depends on the nanoparticle size, it proves that the nanoparticles keep more or less the same size as the initial ones. So they are not agglomerating and growing in size. Same for the printed part. So it's more noisy, of course, but you can see that the position is more or less the same. Here you can see the dispersion from the starting size to the printed sample, that it's keeping more or less the same distribution. And we started first with the silver because of the optical properties, but silver is also quite well known for the bactericidal properties. So it's quite, well, common agent for bactericidal response. Well, it needs to be qualified and it needs to be discussed biosafety in that sense. But well, we wanted to test it for the action against, for example, E. coli bacteria. What we did was not direct test on the surface of the sample itself, but immersing it in a liquid in the growing media of the E. coli, and then using that media where the samples were immersed to grow the bacteria, basically. So we were not killing itself, but we were inhibiting the growth. And here the response, of course, we had a positive and negative test. We have the growing media, the PBS, and we had also the chlorhexidine for killing the bacteria. And then what we did was just immerse one sample of the Pa12, the base polymer, and one sample of the Pa12 with the silver that we were printing. And we could see that the bacteria that were growing here in this petri dish, so in the case of Pa12, they were growing as same as with PBS. In the case of the Pa12 with the silver nanoparticles, so the growth of the bacteria was quite inhibited. So there was a big reduction of the number of colonies. And the final application is different printing method. So this is laser powder bed fusion. But for example, you may know also photopolymers that are liquid polymers or liquid monomers that react to light, to UV light usually, and then they form chains, and then they are solidifying basically. So this is pretty, well, good for us because in the previous case we had to add the nanoparticles to the surface of microparticles. But in this case we already have a liquid and we have colloidal nanoparticles. So what we could do was do the ablation, generate the nanoparticles. In this case we were going for magnetic nanoparticles because we wanted to provide magnetic response to the printed parts. And then we could select the liquid, as I was mentioning at the beginning. We have quite a lot of freedom to select if we want to do it in acetone, in ethanol, and in different solvents. We had to, well, minimize also the amount of acetone to avoid problems with the resin. But we could mix the generated colloid with the liquid resin, evaporate the solvent, the acetone, stir it, and then the idea was to print samples with these nanoparticles, but during printing to add some magnets. Then the magnets, what are doing is to align the nanoparticles in the direction of the magnetic field. So when we are solidifying the material, the photopolymer, the nanoparticles retain this alignment that we are giving thanks to the magnets that we are placing. So well, basically here you see it. I mean, the standard printing technology of this photopolymerization is relatively easy. So there are different technologies, but you can have, for example, a UV, even a diode, an LED. You have a mirror just to displace, and then you go printing layer by layer, and you have lifting, well, here the platform where the sample is retained. And then we were adding this magnetic field, and you can see below, depending on the concentration of acetone that we were adding for the mixing, we were increasing or decreasing the viscosity of the mixture, and then the nanoparticles could move more or less, or align better or worse. Of course, this acetone was also affecting the mechanical properties, so there is like a balance. So you want to align and make larger lines, let's say, of nanoparticles without losing a lot of the mechanical properties. Okay, and here just the last. So here you can see two of the samples that we could print. Well, you can see the versatility that the 3D printing is giving us. So we can print one of these kind of rotors. We can also kind of print a gripper. Of course, in our lab we print a lot of figures from different anime, manga, TV series, everything. So that's, of course, how we try to convince people to join us, and then they need to print rotors and grippers. But these two geometries were quite interesting, at least from our point of view, because the idea was, now that we have aligned the nanoparticles, we can use external magnetic fields to control the movement of these structures. And the point is, you can see here, Okay, first one video, then the other. You can see here, well, you cannot see the magnet, but it's true, I should say, that the concentration of nanoparticles was quite low, so then the momentum, the force that we are generating is not that high. That's why we're doing it also in liquid, but also for a rotor makes sense to do it in liquid. So we can basically control the rotation of this rotor and rotate it one way or the other way around by changing the magnetic field. I will show you how we move the magnets in high speed later. In these ones, yeah, I don't know, we did them without controlling. Here you can see it's a bit defocused, but you can see again the movement, and you can see how we can stop it, and then we can return and change it the other way around. And yeah, the rotor, I like it, but it's only rotating, right? So it seems quite easy to move. But the gripper is a bit more complex. Not complex to let's say prepare it, and you need to be careful of the alignment, but oops, sorry. But the motion itself. So because you have the rotation, of course, but you also have the opening and closing. So we can achieve this movement, so we can rotate the gripper, and then, well, we have a bit of rotation also, but we can open it and close it to grab things. And as I was promising, just to, let's say, close, here you can see also the magnet. So just take a look below. So we have just a piece with the two magnets so that we don't break them together. And what we are doing basically is rotating them. Let me here. So this is fast motion, but you can see how by rotating the magnets, basically we are moving around the gripper, and we are opening and closing it. So it's quite, well, it's still, the force is quite low. I mean, the concentration can be increased. There are things to improve, but it was quite well, interesting demonstrator, and it was quite fun also to to develop it. And then just to finish, a bit of the advertisement also on the research lines. So at least to sum up, I have told about a lot of things. So if you have doubts anytime, just tell me, or we can talk afterwards, or anytime. A bit of the lines that we are developing in the nanoparticle generation research line and additive manufacturing of the group. So, well, we have done this 3D printing of functional materials, like for example these actuators. We are doing also this nano additivation of polymers for bactericidal. We have done also for magnetic response, so we can also do it with powders. Catalytic response. I mean, in principle, you can think about the functionality of the nanoparticles, and we could transfer it also to the material. And with the nanoparticles itself, so we have done works also in this advanced material for sensing, so basically for SERS, generating nanoparticles, and it has been shown that the laser nanoparticles seem to enhance a bit better the signal than conventional nanoparticles. This part of bioimaging and biocidal that we have a lot. And now recently we have a project that we will be developing in the next years that is more focused on thermal applications, on thermal nanofluids, heat management, and also including the additive manufacturing, so printing of heat exchangers and so on. This is to come, so hopefully I can tell you sometime in the future. I would like to thank, because, well, some part of this group was developed by, of this work, sorry, was developed by especially Jan and Ina. So all the group in Germany. That's well, I'm here 1 year, so I cannot. In 1 year, I don't have so many results here. So don't be afraid. And of course, all the group in Spain, in Castellón, that has made very easy to adapt again and to start this new research line. And well, the advertisement, because the deadline is soon. So if you are interested in these topics, or generally in laser processing, because the conference is quite general, so we have this laser ablation, laser advanced material processing conference 2025 in Japan. So deadline for abstracts is closing end of this month. I guess they will extend it, but I don't know. So don't blame me if they don't do it. And we have one special session within this conference that is very general, so you can take a look. That is laser materials processing in liquids. So, well, any topic is welcome, or anyone that wants to know better the technology. It's true that it's a bit far, but well, also it's a chance to visit. So for the PhD students, maybe you can try to convince your supervisors to join. And yeah, thank you very much, everyone. And if you want to get in touch, here you have most of the social networks. Thank you.
Thank you, Carlos. So we have time now for questions, comments, for some discussion.
Thank you very much. So if this is this working? Yeah. So if the size of the bubble that you are generating is an issue, can you increase the pressure of the liquid in order to squeeze the bubble, so then you don't have to move the spot so fast?
There are some people, I mean, with the pressure, I'm not sure if I have seen anything, but with temperature, even people trying with kind of nitrogen liquid, moving to different media, you can control it. The problem is also the balance between the increase of the complexity of the system and the benefit. Because yeah, at some point you want to produce, and you want to produce because we always have the problem of productivity when people come to ask for the nanoparticles. So if we can apply the pressure in an easy way and controlling it well, then it's a good approach. Because some approaches are improving but are so complex that then it's not useful at the end because the price, let's say, or the efficiency is not changing that much. But it's a good idea. Yeah. Also, for example, vibration was another idea. So trying to detach the bubbles sooner. There are a lot of investigation in that direction. Yeah.
Okay, thank you.
Yeah, you're welcome.
More questions? I have several questions, but I will make one in the meantime. Regarding the liquid also, I understand that this will affect the oxidation or the chemical modification maybe that you can induce on the material. So if, as far as I know, I think alcohols inhibit the oxidation, for instance, in comparison to water. Acetone, I don't have any idea what happens with acetone.
Acetone is improving compared to water. It's a media that we use. We need to be careful because of the burning, so you can have some. I mean, usually the system is closed, completely closed. You should have no problems, but I have seen some videos. Luckily, it didn't happen to me, but when there's some coming out, so it could be burning directly. Yeah, acetone and ethanol are the most standard because also due to the price. Because are liquids that are quite accessible. You can use also more complex, so really liquids that have no oxygen at all. But then you again have the balance. If the liquid is extremely expensive, maybe. But yeah, it's possible to use them. The only, I would say, limitation usually is that if you have higher viscosity, these bubbles are more difficult to remove. So then you are reducing the productivity usually. And then also if you have some liquid that has absorption in your laser wavelength, that's of course critical, but or some strong interaction. But yeah, you have a lot of versatility.
And also related to the media in which you are doing irradiation, could you comment something on the fabrication of core shell particles? Because I understand that the one that you mentioned covered by the PEG is in fact the core shell, let's say, or not.
Kind of. You don't see the shell itself. I mean, with carbon, it's interesting, depending a lot on the parameters. Sometimes there are some papers, for example, that they are reporting onion carbon dots. And because they see like a core that is amorphous, and then they have some shell that is crystalline. And for example, they can use the laser and change the structure. So with a, let's say, gentle treatment, not breaking them, so they could change the phase. That's one of the tricky parts I was mentioning also at the beginning. You have a lot of parameters, and then each one is doing one experiment, next person is doing another one, and you can even change the phase, you can change the shell. But for example, yeah, in organic liquids, you tend to have some carbon shell on your nanoparticles. That's not necessarily bad, for example, for alloys, because you can also kind of prevent the oxidation. And in water, yeah, you usually find this oxygen shell. Yeah.
More questions?
Okay, another one. And do you need surfactants to keep the nanoparticles stable, or?
In some cases, yes. In some, not. I mean, it's, for example, with gold, what we usually use is sodium citrate, but really small amounts. So we use like 100 micromolar, and that's enough for the stabilization, for this steric stabilization. There are some other materials that's true. Depending on the liquid and the material, there's no way that you stabilize them, and then you can go to surfactants. But there are also other nanoparticles that you can directly synthesize in the liquid, and they are stable for long. For example, this carbon with the polyethylene. The polyethylene is kind of making surfactant, let's say, because it's covering the surface. Yeah, you have a lot of modifications depending on the material, depending on the liquid. It's a lot of parameters. That's the problem many times. But most of the times you can get some stable nanoparticles out of the liquid and media you want. Yeah.
Okay, but the surfactant is in the liquid before the generation, or you put it afterwards?
Both ways. I've seen both ways. The problem before sometimes, it's also sometimes they have some interaction with the laser. We have seen that. So we try to add them afterwards, but depending on how stable they are, because if they are extremely unstable, then maybe you are generating and directly they are agglomerating and falling. So then you need to add them before. Yeah, it depends on the case, but yeah, the laser interaction with the surfactants, because sometimes you do it and it's tricky to know what's happening.
Yes, another one. And what's the maximum amount of, for example, gold nanoparticles that you can have per milliliter or liter?
Concentration.
Yeah.
Well, directly doing them, yeah, it depends mostly on the laser absorption. You continue generating for a long time. The problem is that you go down and down and down, because every time the nanoparticles that are already generated are absorbing your laser beam. Yeah, it would be like kind of saturation curve with time, let's say, if you continue irradiating. The number, yeah, I don't have the number right now for the gold, for example. But the point is, for example, we have done inks, and there you need extremely high concentration. The point in those cases was doing a flow setup, so that you all the time you have fresh liquid. You just go through, generate the nanoparticles, and collect them. But they just go once through the system.
I was thinking in that configuration. So
yeah,
when do you end?
Yes.
When do you stop your experiment? I mean, if you are a company, so would you be doing the solution with nanoparticles and then send the solution, or is this more thought for the company itself to have this equipment and to generate it in like a?
Currently, there are no companies, I would say, using it. So there was a spin-off from Germany, but it was in the lab, let's say. So it was the lab equipment. I mean, my solution, depending on the application a lot, if the concentration you need is not high, you can do continuous production. Because you can have a big tank of 100 liters, another of 100 liters, and then continue producing this same concentration, let's say. Well, you will need to change the target and move that, but, well, it's minor, I would say. For the inks, for example, we do some recirculation because we don't want to waste so much liquid in that sense. And then an extra step is just to evaporate the solvent and then increase the concentration artificially, I would say. Yeah, the saturation is the only, I mean, the standard concentration that we get with one pass, let's say, it's similar to the nanoparticles, gold nanoparticles you get from sigma algic. So it's optical density of 1 or something like that. So that's easy to achieve. But the saturation, you see something like, yeah, completely purple or really black colloid when you reach that area, but I don't remember now the number.
Okay, yes, final question, just one. Where do you buy the gold? Do you buy the gold in like this in Sigma Aldrich, or do you go to any gold?
We made the mistake of buying from there at the beginning. It's extremely expensive. Now we are buying, I think the name is Agosi, that I found in Germany, that we were using a lot of amounts. It's kind of standard gold seller, let's say, and they can do it as sheet, and it's not costing extra. So it's quite close to the market price.
Okay, good.
Sigma Aldrich is very, very expensive.
Okay, thank you.
Thank you for your nice presentation. My question is about the effect of the wavelength and the pulse duration on your generated nanoparticles. Yeah, because maybe you can avoid the laser photofragmentation by using different wavelengths. For instance, using wavelengths in the UV regime.
Yeah, that's a very good question. The UV regime is usually a problem because of the liquid. Because we have a strong absorption from most of the liquids that we find. And that's in fact one of the problems I didn't mention, but it's fine. Okay. That's one of the problems that I didn't mention, but the femtosecond lasers, for example, for ablation in air, for marking, are really good because you can achieve really good holes, let's say, really good processing. But for ablation liquid, it's not good at all because you have nonlinear effects in the liquid. So you have a strong interaction, and then you are losing a lot of energy. And well, in my thesis, we were exploring some solutions to that, but still, the ideal pulse duration is usually picosecond, because the range where you don't have this nonlinear interaction, so the intensity is not high enough, and then you can avoid these losses. For the regarding the wavelengths, yeah, it depends a lot on the material. For example, for gold, for the fragmentation, green is quite good because the nanoparticles has this plasmonic absorption in 500 nanometers. Then it's very efficient. In general, yeah, the higher the absorption of the material, you will get a better response. But yeah, we always have the liquid. So that's this technique is, we take a lot of results from laser ablation in air, but we need to be very careful because the liquid is changing a lot of things. And then we can profit from that. For example, the multiple beam is nothing new. But the approach is a bit different from ablation in air because it's the bubble and these things. It's a lot to, to study.
Yeah, thank you for your talk. There's a question from the audience online, from Joel Adamas. He is wondering whether couldn't this process be done with a MOPA fiber laser or maybe a UV laser?
So with a fiber laser, right? Or it was UV? Or
MOPA fiber laser or UV laser?
okay. Yeah, UV, the problem of the wavelength is what I was mentioning. So the absorption of most of the liquids, that you are losing most of the energy before it's reaching the target itself. The MOPA fiber, I don't know the speciality of that laser. I mean, with fiber lasers in general, we have worked and it's working good. The beam spot, the M square, for example, is not that critical as compared to, for example, processing in air, because, well, you don't care that much about the pattern that you are generating or the holes you are generating, but about the material. Of course, you want to have all the time more or less flat surface, so you cannot have a completely strange beam. But we have worked with fiber lasers that has lower, let's say, M square, and it was working also good. But I don't know if that specific laser has another specific response.
Hi, do you know why these particles get enriched inside cells? And do you know how long do they stay inside them?
That's a very good question. We need to investigate more into the carbon dots. Inside the cells, we tested, for example, because our first idea is maybe they are dead, the cells. We have some hole, and then they are just going through. We checked it, and no, they were
Is
alive
through
still.
endocytosis or?
I don't know.
Okay.
I mean, this bio part is true that is not my expertise itself, but it's something we would like to know. So if at some point someone is interested in further testing that direction, so we are happy to provide the carbon dots also. So, and also functionalization now you have seen with the sorafenib, with the other molecules also, that that we are getting experience also in that field. Yeah.
Okay, thank you.
Anyone else? I will just ask you the last question. Regarding the alloys, how do you control the amount of each component? Because I understand that it's not only what initial amount, but the ablation efficiency of each of the components.
Yeah, it's challenging, especially for 5 elements like we were showing here. For example, manganese, we were losing a lot. We were studying, for example, with plasma plume experiments in air, so to see how each of the elements was expanding. Of course, we cannot do exactly the same in liquid, but more or less we can. And the manganese, we had a lot of losses. What we are doing is pre-compensate. It's quite empirical at the moment. So if we are having a lot of losses from manganese, then we are adding more at the beginning. Yes. For easier alloys, it's a bit easier, or elements that are closer, let's say, because have similar behavior in the ablation, and then we can get quite same stoichiometry as in the target. Yeah.
Okay. Anyone else? If not, we thank you again, Carlos, and we have a small gift for you.
Thank you very much.